Use mathematical induction to prove that n cubed plus 5n is a multiple of 6 for all n in the natural numbers. So as long as n is a natural number, this should be a multiple of 6. As always with proof by induction, we start with step 1, which is our base case, which in this case is when n is equal to 0 because we're in the natural numbers. When n is equal to 0, we get 0 cubed plus 5 times 0, which is equal to 0, and that is indeed a multiple of 6. It is 6 times 0, and therefore the statement holds when n is equal to 0. Now we move on to step 2, having shown the base case, which is our assumption, when n is equal to k. We assume that k cubed plus 5k is a multiple of 6. Algebraically, that means that k cubed plus 5k is equal to 6a for some natural number k, a. With our assumption made, we move on to the inductive step. This is where this one becomes a little bit more tricky. What we want to show is that k plus 1 cubed plus 5 lots of k plus 1 is equal to some multiple of 6. So let's have a look at that. How can we manipulate this? Well, one way would be to expand this whole expression out. It's doable. You'll have to use binomial expansion to expand k plus 1 cubed or expand it longhand. But actually we can be a little bit clever here and do a little bit of factorizing, because these two terms have a common term of k plus 1. So we can factorize out k plus 1 at the front and then think, what do we have left? Well, k plus 1 cubed, we need to multiply k plus 1 by k plus 1 squared. And 5k plus 1, we need to multiply the k plus 1 that we have by 5. Now, inside that second bracket, we now have something which is much easier to expand. K plus 1 all squared is k plus 1 times k plus 1, which is k squared plus 2k plus 1. But then we have this plus 5 at the end, so that is plus 6. Expanding this, we now get k cubed plus 2k squared plus 1k squared, so that's plus 3k squareds. Then we have plus 6k plus 2k, so that's plus 8k. And then the constant term is plus 6. As I said, we could have done this in a different way. We could have expanded k plus 1 cubed and then simplified it. We would have got to the same thing. It doesn't particularly matter how you do that to get to there. Now that we've got this, we're trying to think, well, at some point we know we're going to have to make a substitution. We're going to have to somehow substitute this in. Well, let's make this look a little bit like that. Let's say that we have k cubed plus 5k. And then what do we have left? Well, we have a 3k squared. We've used 5k, but we have 8k in total, so that's 3k. And then a plus 6. But this k cubed plus 5k is equal to 6a. Now we can make the substitution. That is just equal to 6a from our assumption. So now we have 6a plus 3k squared plus 3k plus 6. Okay. Well, what can we do with this? Well, we're trying to show that this is a multiple of 6. Now, we have 6a and 6 at the end. They're definitely multiple of 6. But in the middle here, we have 3k squared plus 3k. That's a multiple of 3, but not necessarily a multiple of 6. So let's see how we deal with that. Let's keep the 6a for now. And what I'm going to do is I'm going to factorize this to get 3k times k plus 1 and then plus 6 on the end. And what I'm going to notice at this stage is that I have k times k plus 1. K times k plus 1 is 2 consecutive numbers. Because it's 2 consecutive numbers, one of them must be even. And if one of them is even, then the product is even. Because an even times by an even is even, and an even times by an odd is even. So that means k times k plus 1 is an even number. Well, that means we can write it as 2 times something. So this is 6a plus 3 lots of, well, instead of k plus 1, I'm going to write this as 2, let's use a new letter, c, because k plus 1 must be even, plus 6. Now we have 6a plus 6c plus 6, which is equal to 6 lots of a plus c plus 1, which is equal to 6b, which is our right-hand side. We have shown what we wanted to show, that k plus 1 cubed plus 5 lots of k plus 1 is a multiple of 6. Finally, we finish the proof with step 4. Our conclusion. As always, our conclusion says pretty much exactly the same thing, which is because we're using mathematical induction, the statement holds for n equals 0, and if it holds for n equals k, it's also true for n equals k plus 1, so it is true for all natural numbers. Let's quickly review that inductive step because there was a tricky part in here. In particular, noticing this. Noticing that k times k plus 1 is equal to an even number. There was another tricky part earlier on, the green step here. It wasn't a direct substitution for our assumption, or not as obvious as in other cases. We made what we wanted and then dealt with the rest. And sometimes we have to do that in maths. Sometimes we have to, well, I know I want to make this substitution, so let's make it so I can make that substitution and deal with what comes next. Similarly here, I know I want this to be an even number because I need this to be a multiple of 6. So how can I argue that that is an even number? Oh wait, it has to be even because it's the product of 2 consecutive numbers. There are a few other ways you could have approached this step here. You could have gone with if k is even, then k squared is even and k is even, so both of these would be even. Or if k is odd, k squared is going to be odd and k is going to be odd. So then you get the sum of 2 odds, which must be even. It's a little bit longer to write that out than this one, but it would be fine to do it that way as well.